Good morning. Those of you, just a show of hands, who's heard any of my talks before? Just a show of hands. Who's heard any of my talks before? This is a new one, so some of the images will be similar, but it's a completely new presentation, so there, one, won't be any issues about the PDH credits. And thank you for coming. This will be building oriented. I'll show you a couple of things just to whet your appetite in terms of other directions things go or can go. But in order to do it in the 1 hour time frame, and I set it as a focus on buildings. What I want you to come away with from this is an understanding of the physics behind infrared or IR. And I'm going to spend a little more time on that than I have in the past. I want you to know the major applications to buildings, as well as understand how those applications work and what the field procedures are for actually performing them. Infrared is light just beyond the red in the visible region. Visible light is 300 to 700 nanometers, or 0.3 to 0.7 microns, or micrometers. A micron is 10 to the minus 6 meters. Infrared goes from that 0.7 out to many microns. It depends on where your level of interest is. Typically out to 20, 25 microns is certainly an accessible area for infrared. It can, in fact, sometimes be defined out to, say, 100 microns. Thermal infrared varies with the temperature, but is roughly from 2 to 14 microns for most applications that will be of interest to this group. Thermal infrared is emitted by all objects above absolute zero. The peak wavelength that's emitted is related to the temperature of the object. As the object gets hotter, the wavelength gets shorter. So if you take a piece of cold iron and you begin to heat it, it emits shorter and shorter wavelengths and more energy, and eventually it starts to glow, and you've all seen this. The peak wavelength is now in the visible region, and the glow of iron typically would start in a deep purple magenta, move in through the red, yellow, and white as it gets hotter and hotter. And this is something you've all observed, if nothing else, on resistance heaters when you warm up the bathroom on a cold day. The energy of the emission increases as the temperature goes up as well. And this characteristic of a different peak temperature and a different distribution and a different level of energy allows us to differentiate the temperature of object A from object B because of the differences in the characteristics. An ideal emitter is defined as a black body and has an emissivity of 1. And emissivity I've shown here as E, it's typically written as epsilon. So when you see epsilon equals 1, which you won't see on my presentation, they're talking about the emissivity. Real objects are compared to a black body by their emittance or emissivity. It's always less than 1. And it ranges from 0 to 1. A 0 emissivity means that the body emits no infrared. Nothing gets down to that. That would be a perfect reflector or a perfect transmitter. Nothing, as you know, is perfect. Real objects have an emissivity less than 1, and we idealize them as saying that they're gray objects, which means that the emissivity is independent of the wavelength. Real objects are not gray, and they in fact have an emissivity that is dependent on the wavelength. There are 3 components to the infrared that leaves the surface of a body. The emission, in other words, what the body is generating as a result of its temperature and its emissivity. Reflection, which is what's hitting it from outside and bouncing. And if the body is transparent to any degree, what's coming through the body from what's behind the body. Emissivity plus reflectivity plus transmissivity is by definition equal to 1. So if you have an opaque body, 0 transmission, and let me caution you that things that you think of as opaque in visible light are not necessarily opaque in the infrared, and vice versa. but let's, for argument's sake, say the transmissivity is 0, and most of the things you deal with in buildings, with the exception of glass windows, that is true for. The emissivity plus the reflectivity equals 1, so the more reflective it is, the less emissive it is. The more emissive it is, the less reflective it is. And if you have a highly reflective object, what you're really seeing when you look at the object is not the object's emission, but what it's bouncing off of from what's behind the observer, essentially. Just some graphical representation. You have wavelength representation there, and you can see you start with radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray, shorter and shorter wavelengths. In terms of frequency, the middle presents that. And in terms of temperatures at which these various wavelengths would occur, you can see the second bar from the left at 100 Kelvin here is about 10 to the minus fifth, so like 10 microns. If you get up past the visible, actually into the ultraviolet, you're now looking at a temperature of 10,000 Kelvin, which is, even though we're in the US, I'm sure you all know, is extremely high. The two laws, if you will, the laws of physics that present this are Planck's law and Wien's law. Planck's law describes the shape of each of these curves, and the different curves are for different temperatures of an object, treating it as a black body. The equation up in the upper right is Planck's law. And the things to see here in terms of the characteristic, and these are all relatively high temperatures, but the characteristic is that as the temperature goes up, the distribution gets narrower, the distribution moves to the left to shorter and shorter wavelengths, and the peak energy gets higher and higher. This is also true as we go, further to the right in lower temperatures, body temperature, room temperature, and the like. Wien's law, which is the equation in the text on the left, describes the location of that peak. So it's the curve going down through the peak. And it tells you for various temperatures in Kelvin, divide 2898 microns by that temperature, and you get the wavelength of the peak. Typical values that you'd encounter: cold weather temperature, in other words, 0 Fahrenheit, has a peak at about 11 1/3 microns. Room temperature, just under 10 microns. Body temperature, about 9.5. Oven temperature for a moderate oven, would be about 6.4. And furnace temperature, where I've defined the furnace as 1500 Fahrenheit, just as a number, 2.66 microns. And you can see this covers these peaks occur in that 2 to 20 micron range that we're kind of calling the thermal infrared. As you get hotter than the 1500 Fahrenheit, you get shorter than the 2 microns, and as you know, eventually things become visible. Okay, this is a PDH presentation. What's the approximate wavelength of thermal infrared as used? Sal? Okay. As objects get hotter, what happens to the radiation they emit? Ralph? Anybody else? Wavelength gets shorter. What else? And what else happens? More radiation. Okay. IR cameras detect and directly report temperature. True or false? Now you're going to have. I didn't really discuss. I didn't. False. Okay. What they detect is the radiation. We interpret it as temperature by looking at what's the temperature being bounced, reflected from it, and what's its emissivity and reflectivity of the object that you're looking at. At a given temperature, all objects will appear the same to the infrared camera. Why? At a given temperature, all objects will look the same to an infrared camera. Absolutely. So for example, if I take a shiny aluminum fry pan and I paint half of it matte black with a high emissivity paint, and I put it on the stove, and I get it up to frying temperature but dry, and I look at it with the camera, the shiny aluminum side looks like it's about 70 Fahrenheit. The matte black side looks like it's about 500 Fahrenheit. You know they're the same, pretty close to the same temperature. They may not be exactly the same because of some secondary effects, but they will look vastly different even though you got one object that's at a common temperature. Okay, 2 to 14 or 20 microns, which we said. As the objects get hotter, the radiation increases in intensity, shortens in wavelength, and eventually becomes visible light. The cameras do not detect temperature directly. They detect radiation and with help interpret it as temperature. And that help can be critical because if you don't help it correctly, you get bad answers. At a given temperature, you do not have all objects appear the same because of emissivity, background temperatures, and transmitted radiation temperatures. So if you have a moderate emissivity object, say 7/10, two of them side by side, and one of them is seeing a 1,000 degree furnace behind me as I'm looking at it with the camera, and the other one is shielded from that as seeing room temperature. They're identical, they're at the same temperature, they will not look the same even though they have the same emissivity and they're at the same temperature because the reflection has changed. Okay? All right, here's a shopping list, if you will, of selected building applications. In terms of energy audit type work, there's insulation condition, whether it's there, whether it's properly installed, what condition it's in, and air leakage. In terms of water detection, you can look at the building envelope, including the roof, and in particular low slope or flat roofs, not really peaked roofs, and you know, a roof with an attic, a home roof with an attic under it. Interior walls and other surfaces. You can find, if you do it properly and if you're lucky, subsurface features, and these can include building components such as pipe, the lamination of masonry walls or other walls, spalling of walls, voids in objects such as walls, and radiant heating systems and the piping in them, or piping behind walls, which is really the first bullet under that. Additionally, you can use it for construction confirmation, and you'll realize that that entire list up to there can include construction confirmation. Did the contractor put the insulation in properly? Did he air seal the building properly, etc.? And it can also include CMU pilasters and insulation testing. Are the pilasters where they belong? Are they continuous? Do they jog when you go across the bond beam? Did they forget some? Etc. All right, let's look at a few images as examples. This is the exterior of a high-rise in Manhattan. The area here has a pipe chase behind it. The warm area at the bottom floor in the image, which is about 7 or 8 stories up, averaged 12 degrees hotter than the next floor up. Now, I don't know the actual happenstance that led to this, but my supposition is that the crew went to lunch at the bottom of the image and came back 1 floor up and just missed the floor. They did not insulate the outer wall of that pipe chase. It could have been a Monday, Friday thing, too, like, you don't know for sure. The next couple of images are from one particular project. This is again exterior, and you can see the warm areas, part of which are next to a joint, a change in the facade, but part of which are also along where the insulation board would be behind it. Same project, same buildings. All those warm areas are problems. The possible exception, but probably not, is that very hot area right up at the top there in the inside corner. Inside corners are protected, so they're radiating at each other, so they're not radiating to the world as much, so they're not cooling off that way as much. They are also protected from wind currents, so you will tend to see greater warmth in a protected area. So you'd expect a little more warmth on the inside corner and more beyond that in the three-way corner. That looks extreme. Well, if it's coming from the inside and leaking out, it could be doing that, and that's a problem. It's not supposed to leak out, yeah, all right? Remember, this is the exterior. These are photos from the same project. And the reason I was on that site was they had 5 buildings that had recently been built, and they didn't think the contractor did it right. They did, I think, 33 removals. These are typical of them. And you can see the gap above the insulation board below the relieving angle. You can see the hole where there should be insulation board, but there's just poly mesh. Of the 31 removals, 30 were like this, and one had another really clear reason for showing a hot spot on the exterior. All right, this is an infrared image and a photo side by side. The infrared is on the left. You can see the cool areas on the exterior wall, the cool area in the second floor ceiling. This is a private home, so there's an attic above it. And in fact, if you look carefully at the photo, you can see there's actually a dark area in the ceiling corresponding to the cool area, being caused by cycling over 2-3 years, where you get a little more deposition, a little more condensation on the cool area, and it makes it dirty. So you've got dark is cold and dark is dirty, showing you the same location. Two infrared images, photo of the same area. That's the light switch up above, and that is really showing you air infiltration. And you can see the temperature ranges there. The blue box is the measurement area. You can see it's ranging from almost 61 to 67.5. That's a pretty big temperature change on a small area of wall. We don't see the air. What we see is the impact on the air on the temperature of the surface. So if air were coming through a hole straight into the room, the only thing we would see is that the edge of the hole should be cooler than the area next to it. But that is not the case here. It's impacting all the surfaces around the switch, and we are therefore see where the cold air is coming in. You see in the corner of the room in the other image this large vertical cold, which is most likely steel column. Not necessarily something they can easily avoid, but depends on how hard you want them to and how much you're willing to pay them to do so when they build. Two more examples. On the left is somebody's living room. You can see the studs, and on the left side of this image, the studs are visible but not obvious, not terrible. That's normal. The studs, whether they're wood studs or even more so metal studs, are more conductive than the insulation between them in an insulated wall. That means if it's cold outside, the inside surface of the stud will be cooler than the area between them. The reverse happens, by the way, if you got no insulation at all. If you've got an empty bay, the stud is more insulative than the air, and the studs look warmer. Now, the studs over on the right side of that image are much wider and colder. The insulation wasn't brought to the studs the way it should have been. So you got an issue there of insulation, installation. And in the middle, I probably don't have to point that out to you, but I should. Those large cold areas are problems where the insulation either was not put in, was put in poorly, has sagged since it was put in. You'll note, by the way, that you can even see the studs through the picture hanging on the wall. Not as clearly, but there's enough difference that it's carrying, the temperature difference is transferring through that as well. It's better to look at the bare wall when and where you can. The other one is air leakage coming through what's actually a patio door, but could as easily be a window. And again, you see the influence of the cold air cooling things off. Right. These are the same image, just one in a color and one in grayscale. In the field, we tend to work in grayscale because it's easier to see what you're doing. Color emphasizes the temperature differences a little better. But it's all perception, because you're mapping, your color mapping or grayscale mapping something that we can't see. And that's what the camera's doing for you. There are two issues here. One is the air streak coming in from the cornice or the eave. The shape of it tells you it's air. The other is the ceiling light. Many ceiling lights, less so now than previously, required no contact between the light in the ceiling and the insulation. You had to have a boundary around them. But it was a boundary around them, which this is not. This is flush to insulation on at least one side. And the boundary, no way should have been as large as that. So this is a misinstalled lighting system or misinsulated lighting system. All right, how do we do these? Those are samples. How do we go about doing them? Generally, when you're looking for insulation issues, it's a passive exam. You look at the building as the building is. You don't have to do anything to the building. You do need to make sure that you have an adequate temperature difference between the inside and outside, and that's typically a 20 Fahrenheit difference or more. If you got more, you see it more clearly. Air leakage, which is equally important for both comfort and energy, can sometimes be seen under natural conditions. You will get some air leakage just as the building sits. And that sample I showed you of the ceiling was the building sitting and air was just, whether it's because of wind or stack effect or the like, there was air leakage. I didn't do anything to generate it. Generally, however, we incorporate the use of a blower door, which is a large fan calibrated in an expandable frame that fills the doorway of a house or a building, and then either depressurizes the building, forcing air in through any of the leakage paths, or pressurizes the building, forcing it out through any of the leakage paths. When you depressurize the building, you look at the inside and you see where the cold air is, where the cold areas are. And when you pressurize the building, you look at the outside and see where the warm areas are. All of that based on a cold weather inspection. You can do it in hot weather as well with an air-conditioned building. Generally, we look for a 50 Pascal differential. We can run to less than that and correct to the 50 Pascal, but 50 Pascal is kind of the industry standard point for air leakage evaluation. And we can then rate the building in terms of air changes per hour and compare it to published standards. If you're only looking for air leakage, you can in fact get by with a smaller temperature differential, as low as 5 Fahrenheit. More is better. This is a picture of a blower door. You see the fan on the bottom. This particular blower door has a nylon panel with a view window, so you can see if somebody's trying to come through the door. Not shown on this is the instrumentation package that goes with it that tells you the differential pressure and the flow rate through the fan. As shown, the fan here has a cover on it, which has to be taken off either in stages or completely to actually run. The way it's shown, it's still sealing the house the way a closed door would. There's a fair variation in the field approach. I've seen people say, we just come in and take pictures and move away. And frankly, I can't get behind that for most applications. The best information is obtained by going to the building under as-is conditions, preferably at night when the sun is not in effect, because if you got sun shining on the outside of a wall, that outside surface gets hot, and potentially, even though it's cold outside, you got heat flowing into the building, net flow, and gee, you see all the nice warm areas on the inside. Well, if you see warm areas on the inside when the heat's flowing in fact, you got a problem, and you're going to interpret it as, oh, that's the area that's good. So you do need to be aware of when it's done and what the surrounding conditions are. My preference is to do an interior scan, essentially, and again, I'm talking cold weather, looking for cold areas. Do an exterior scan looking for warm areas. Set up the blower door. Get a reading with the blower door in terms of how much air change there is. Repeat the interior scan with the blower door running, so I now have augmented conditions for the inside, looking for cold stuff. and then reverse the flow on the blower door, pressurize, and look at the outside. Again, augmented conditions on the outside. The difference between the interior scan without the blower door and the interior scan with it is ascribable to air leakage. Some of what you see without the blower door is also air leakage, but not completely. Most of it is insulation, plus a little bit of air leakage, and then the difference, okay, that's air leakage. Often the shape of what you see is informative, but not completely and not always. Doing it this way allows you to see what those differences are. And as I said, you need to pick when you do it. And since you end up doing it at night, a lot of people aren't all that happy, especially if it's a residence with little kids. But they gotta go to bed. All right, let's look at some examples of water detection. We'll look at both roof moisture surveys, and these are primarily flat, what are officially called low slope roofs, but what most of us think of as flat roofs, and it's really what the consumer thinks of as a flat roof, and wall studies, both interior and exterior. Roof surveys are almost always, if done on top of the roof or from a plane, are generally done at or around sunset, and I'll bring that out later. And the wet area, what you're looking for is wet areas insulation. If you have a small hole in the roof, liquid water is getting into it, it's being absorbed, hopefully if you have absorptive insulation, which is not always the case. So the insulation now is wet. As the roof cools off at night, both by convection and radiation to the night sky, that water stays warmer longer, and you're looking for that differential. So this is a transient, but one driven by natural conditions rather than one that the thermographer applies to the system. And you can see where the warm areas are marked. The E7 and I1 and so on is the image numbers, so that when I get back to the office I can say, okay, that image is there on the roof, and you can come back in daylight, or if you have a good flash on the camera, you can take a picture, so you get both a photo and a infrared image comparison. You got two infrared images, two presentations of the same image, again color and grayscale, and a photo of the same area. Looking here for both moisture and delamination. This was done with the sun shining on the surface. Been on there for about an hour, hour and a half. And what you end up seeing is the dark areas that are not ascribable to visible impact. In other words, you can see this building's been patched a fair bit. And it's not a new building, this is a 1920s era building. It's stucco over terracotta, and it helps to know what your construction is. But there's nothing visible corresponding to this cool area. Probable water. There is some correspondence, so this is probably just a difference in the patch, although the patch doesn't quite run contiguous the way this does. So you got a possible problem here. This bright area, these bright areas represent delaminations. A piece of the wall that is not well attached to the part of the wall behind it physically is also not well attached thermally. So that if you have, and now here's your wall, I'm going to turn it so you can see the cross section. There's a piece of delaminated wall, you got the sun shining on that. The heat flow path for this section is into the skinny little piece and then around the delamination. So it's a much longer flow path than straight through as it is in the areas next to it. That means that this area can't absorb the heat, can't dispense, can't get rid of the heat as quickly, as readily as the other areas, and it gets hot under an applied load. Similarly at night, the building is not feeding it, so it actually cools off faster. And I'm going to show you some graphs that explain this. The same building, you can see the bright spots over the top floor window, below, next to the air conditioner on the bottom left. So those are delaminated. Around the air conditioner on that middle floor, you can see the large cool area to the left of the air conditioner. That would be water. And you got an identical row of quite rectangular cool areas next to the windows that tell me that this building used to have wider windows and they filled it in. Okay, so that's not a finding, although it was news to the people who own the building. Here's the lower arrow points at a hot brick. Again, this is with, and you can't interpret this unless I tell you this was done in mild weather with the sun shining on the wall. You need to know what the conditions are. But mild weather with the sun shining on the wall, you've got a brick that's turned hot, and you've got a whole area that's turned cool. The hot brick is not well attached to the wall. In other words, and they did some removals here as well, and rather than mortar behind the brick, they had what had been mortar but was now a pile of sand. And the issue with this building is that bricks were falling out of the facade. At the same time, we were finding water in the walls. This is an interior. It's a ceiling not quite under a bathroom. On the upper left one, the one in the blue image, if you will, you can see there's a real cool spot representing wet. There's a close-up of it here with the pointer kind of pointing to the fact that it's not even and that you have some additional but not as severe cool moving off towards the right. That's what happens after you've applied heat to that surface. The areas that have some buried water below the, in this case above the surface, it's the ceiling, beyond the surface, don't warm up as readily as the area surrounding it. So it gives you a handle on what direction is the water coming from. And on the photo, you can see I put some blue tape on to mark the spot. But other than the blue tape, there is nothing visible that tells you here's a wet spot. This is the ceiling in the United Nations General Assembly. They had roof problems and they wanted to see whether they were pretty well gone. This is an acoustical tile ceiling. That spot in the middle is a hi-hat, a light. So the bright area is just the reflection off the cover. The light is not an open, it has a half cover on it. But you can see very faintly the cool areas in the joints of the tile. So there was still some moisture in that ceiling. All right, those are the examples of the water detection. How and why do they work? One is if the water is not trapped. In other words, if it can get to the surface and evaporate, you see it by the effect of evaporative cooling. And that's what we saw in that ceiling case where without doing anything, the nice blue spot was a cold spot representing water evaporating and making the local area cooler. If it is trapped, and a roof is an example of trapped water under the membrane, you can have a pinhole in a roof and you can fill up many square feet of insulation with water. You make that insulation wet, the water is not going to get back out of the roof. It gets in, it doesn't come out. So you have a situation where you've got trapped water. It can't evaporate. It's not going to evaporate up through that pinhole. It's not going to evaporate through the membrane, and it's not going to evaporate down through the deck. So it's there. But the only way to find it is by a transient, where essentially you apply heat, everything warms up, you let it cool, and the high thermal mass of the water makes it stay warmer longer. And that's what happens when sun shines on a roof and the sun goes down and the roof starts cooling by radiation and convection to night conditions. So it is active thermo... I'm sorry? It's not actually warmer, it's just not as cold as everything else. All right, so I've touched on this. The evaporative cooling, it's there. It's not the temperature change, the temperature difference, the anomaly is naturally occurring, so you see it by itself. So essentially it's a come in and look rather than do anything more. And an interior wall or carpet or water under carpet would all be typical applications for that. Trapped water, you need a transient. It's nicer to use natural occurring transients, such as sunshine, such as a diurnal temperature change. And you saw examples of that both for the delamination water combination where I show you that stucco building over terracotta. You saw it on the one with the loose brick. However, if you can't get a transient, if it's late November and you're looking at a north wall, you're sort of in trouble. Some of these are very weather dependent, both in terms of scheduling or even seasonally dependent in terms of being able to do it at all. The next step is to say, okay, how do I apply a transient to this? You know, lights, blowing hot air on it, depends on what the need is and what the scope of the inspection is. So, the field procedure, the simple cases, go take pictures. Exterior walls, roofs get a little more complicated, and I've indicated that to you. Interior walls, my preference, again, if you will, belt and suspenders, is look at it, do something to it, induce the transient, look at it again, so you can look at it change from before and after, because changes are more informative than, well, I see something, but I don't know if it's an anomaly of the type we're looking for. The lamination generally requires a transient, and the lamination is essentially, you know, the wall looks like this. Where possible, solar loading is a very nice transient, and the procedure and timing for an exterior wall, at least, is very similar to when you're looking for water in that wall. So you tend to find both water and delamination at the same time. That's a little dependent on how deep is the water or how deep is the lamination and what the physical properties of the wall are. If it's brick or if it's concrete or if it's stucco, they have different thermal properties. So you do need to be concerned about that. You can't guarantee that the water and the delamination will show up exactly 45 minutes after the sun hit the wall and within 10 seconds of each other. I described this already to you. We're detecting delamination or voids or bad material because of the difference in their heat transfer characteristics. This, you know, so far we're, quote, looking at temperature, taking pictures really of radiation, but, you know, the approximation is we're looking at temperature. And as engineers, you know that the temperature got there by heat transfer, which means that if you do a heat transfer analysis, you can get a handle on what's going on and how it happens and how it occurs. When should you be looking at it? What, if you saw this, what did it mean? And what I'm going to show you now is, you know, example of an output from a finite element analysis for heat transfer of a wall. This is, in fact, that wall that I showed you with both the delamination and the hotspots, the stucco over terracotta wall. This is for a southeast exposure at a particular time of year, June, July. And you can see the green is the delaminated area. Each curve represents either delaminated wet or normal wall. The wet wall is the magenta, and you can see it has the least swing from nighttime, and this goes from 0 hours to, well, 4 in the next morning, 6 the next morning. But you can see at night, before the sun gets started, before the air temperature goes up, the wet area is the warmest, and during the day, the wet area is the coolest. Similarly, at night, the green, which is delaminated, is the coldest at night because it can dump heat, the most heat per mass to the outside because it's not being fed from the inside. And at night, in the daytime, it's the hottest because it can't get rid of the heat you're applying with the sun and air temperature. The independent data points are data from the infrared, which match fairly well. The part that is particularly good is the fact that the orders reverse on the infrared the same way they reverse on the curves, and at about the right time. So, you know, the analysis is a good guide. It's not something that you're going to go out and say, all right, we can design this or design the work so that we look at it exactly 23 minutes from when the sun hits it, and we can be done by 27 minutes. No, it tells you, you know, you need about a half an hour to 45 minutes of sun, and then you can look at it. You may need to stay there for an hour. Tom?
The lines are the FEA?
Yes. And the large data points are data. Yes. All right, so this is a southeast exposure. Now, the nice thing about, you know, computer analysis is you say, well, what if? And you can change one parameter, which I'll show you after this graph. This is the contrast which is the temperature difference between adjacent areas for wet versus dry and delaminated versus dry. And you can see, one, the peak difference occurs at different times and is in the opposite direction. Now, we've already discussed the fact that it'll be in the opposite direction. The wet area is coolest at the daytime, warmest at the nighttime, and the delaminated does just the opposite. So this is what the thermographer would look at and say, okay, you know, I've got a temperature difference here of 10 to 15 degrees. I can go out and find this. But if you go back and say, well, you know, I've only got a difference of half a degree, I need to do something to the wall, or come at a different time, or do something other than what occurs naturally. This is a west wall, same building, same time, you know, time of year, same atmospheric conditions, same solar characteristics, and you can see it's the same but different. It's the same in that the nighttime wet is the warmest, daytime wet is the coolest, but the shape of the curve has changed because the sun gets to the wall at a different time of day, but the wall is still seeing the air temperature changes at the same times as the southeast exposure did. So you got a different shape, it's offset. It tells you, well, you know, if it worked okay on the southeast wall at 10 in the morning, you need to be on the west wall at 3 in the afternoon. This is the model of the wall that produced those FEA results. And what you have are 3 sections. The bottom third is a delaminated wall, and you can see this thin blue section here is the air representing the space. This is a wet area, and this is a dry area. And I did them all at once. One, so I could only run one model. And two, it also tells me, you know, what happens at the boundary. How muddy do the results get because you've got good and bad areas next to each other. And one of the nice things about it, and it's useful from the standpoint of you get to understand things better, is you can actually animate the results from the FEA. And this is temperature over a 24-hour cycle. And you can see as the sun comes up, and now the bottom area is getting much hotter than the other area. That's the delaminated area. You can see that the temperature differentials, now it's cooling off, the temperature differentials here are much bigger, over a much bigger area than here. Now at night it becomes much colder, and I'll let you watch that again since it's short and you can't object. Exactly. The interior is the backside. And you can see it, you know, as it cools off, heat is actually moving in both directions. As it warm, you know, heat's moving in both directions from the core. So that gives you a handle on what it's doing. Wrong one. You can also look at a vector representation of the flux rather than just the temperature, and that's what I'll show you now. Exactly the same simulation results, but now plotting flux. And you'll see that as this doesn't have the timestamps on it, but it's running at the same speed. You can see there's, as the sun comes up, there's a lot more action, and down in this area, the heat is going up and over, rather than straight through as it, you know, as it's going in the other areas. So you get to understand, well, what did I see and why did I see it? This is often very helpful for that, or what should I expect to see and why should I expect to see it? So the finite element analysis is a very good handshake with the infrared. Guessed right. All right, construction confirmation, as I mentioned before, is another application, and you know, it's did they build it right? Did they build what you told them to build? When your back was turned, did they keep doing what they were doing when your back wasn't turned? And it addresses insulation, air sealing, and CMU pilasters as major items. CMU, concrete masonry units, and do I have to explain? Does anybody not know what a CMU is? If you prefer. I'm not going to argue with you because I know you're being facetious. This generally requires a transient, and that would be, you know, the transient of choice, again, is day-night solar loading changes. If the grout in the pilasters is still generating heat because it's curing, you can see that signature, but often that's not the case. So, you know, unless you're actively following the pores day by day, not the way to go. The empty blocks, the empty cells in the blocks respond differently than the filled, and this is both a thermal conductivity and a thermal mass issue. Generally inspected at night, the filled cells show up warmer because they're holding the heat essentially, and you can detect both the continuity of the pilaster and the alignment of the pilaster. One of the problems that sometimes happens is they build, they pour, they build, they pour, they put in a bond beam, and they pour, but they forgot which cell they're supposed to be filling, so they pour over here. And you have a pilaster that looks like this across the bond beam, and that's not a good thing. And if you have appropriate instrumentation, as in a sufficiently sensitive camera, you can also see whether and where the cells have been insulated, which is, you know, often done essentially with a foam insulation. I'm not sure how much I actually have on here, but I have done, I'm not going to show the animations for this, although I'd like to. But I've looked similarly to the sample I showed you. I've done that for CMU wall. Actually had data from a 24-hour cycle that a colleague had done looking at both the interior and exterior walls of a partially finished project. And he had mislabeled it when he sent it to me, and I ran the simulation and I called him up and I said, Greg, you know, there's something really wrong. He says, oh yeah, I mislabeled them, it's the other way around. So this FEA stuff works, but it shows the crossover. The filled cells are not always warmer. They're warmer when you generally go out and look at them, which is, you know, late evening, wee hours of the morning. And the contrast, which is a temperature difference between the area of interest to an area next to it, which is what you can detect with the camera, is the guide to will you find it and how will you find it. So let's take a look again for a specific time of year, specific orientation. And this is for the interior of the wall, which will have a smaller contrast than the exterior because the sun hits the exterior much harder than goes on the other side. This graph combines both field data, which is the stuff with the data points on it, and simulation results, which are the smooth curves. And you're looking at both temperatures and temperature differences. But you can see that things track fairly well. They're not exact, and they're not really expected to be. But you can see that you get temperature differences. The large dots, the large brown ones are data for filled versus empty. And you can see, you know, in the late afternoon or in the afternoon, filled minus empty is negative 1.5 degrees. And around midnight, it's plus 2 degrees. Okay, so it has flipped. You need to know when you're looking at it and what to expect for that type of wall. That's the contrast, and you know, these are your temperature traces actually over a 48-hour run of the FEA. Does anybody think that this is a good wall? All right. The warm areas, the bright areas, are filled. The dark areas are not. This was taken by the same fellow who gave me the data that I compared that FEA against. And as he says with his southern accent, it's supposed to look like a jail cell. If it looks like a bar graph, it's screwed up. This is beyond looking like a bar graph. This is a disaster. This is, guys, start over. All right. Across the top is a composite of multiple images Essentially, you know, this is like a Lowe's or a Home Depot type big box store. And then some examples down below. On the left image, you got pilaster problems, which I've circled. So you got a pilaster here that stops and resumes. You got a pilaster here that stops and may resume. You got one here that stops and resumes. You got an uneven fill of the bond beam there. On this other image, and this is harder to see and harder to reach, you can see there's a slight, can you see that there's a slight difference in the color here, here, and here than the areas immediately next to them. Is that visible? All right, and that's the insulation or lack of insulation in the non-pilaster, non-grouted, but insulated, allegedly insulated cells. Standard application for infrared is to look at electrical distribution systems for hotspots, and you're going to find poor, weak, corroded, or overloaded connections or failing components. And they will be generating heat because they've got more resistance to the flow of the current. So it's a comparison. You look at 3 of them, and if one of them is hot and the load is the same, you've got a problem. Energy systems for insulation, in other words, your piping and your steam systems, your boilers, hot water distribution systems, they should all look fairly uniform, preferably cooler rather than warmer, but you don't want to see hot spots all over them. And you can also use infrared, as, for example, to look and locate piping in walls, underground, and other instances. This is a high temperature hot water distribution system at the Hunts Point Market in the Bronx. Note the difference in the temperature scale. The one on the left is 0 to 120 Fahrenheit. The one on the right is 23 to 38 Fahrenheit. These are taken at the same time. They knew they had a problem over here. I mean, they can't even keep snow on the ground there. I lost a job that way once. They said, we can find it because it just snowed. Well, thanks. So there's a clear problem here. But you can also see, where is the pipe? You can see that the elbow, partially because it's an elbow, possibly because it has a thrust block there, is warmer. You can also tell that, you know, the guy who drives this third car got to work much later than anybody else. All right, just a couple of examples, and these are a small sample of what you can do with infrared. I like to say that, you know, the applications for infrared are only limited by imagination, the clients in mind. This is from a plane, and you can see that there is a seep here into a body of water. Whether it's an illegal seep or not, I don't know, but it's there. Any 2 pieces of water on the ground surface tend to be different temperatures, so you can find them this way. This is a process vessel, approximately 160 Fahrenheit inside, fiberglass. All of those cooler spots, and this is about an 8-foot diameter. So those spots are maybe 12 inches. Every one of those turned out to be an incipient failure. You were getting delamination, so there was either a bubble with air, or a bubble that had burst and filled with product, in this case pulp, which was more insulative than just the wall, because you had wall plus however many inches or fractions of an inch insulating it, and therefore was keeping the heat. You know, this spot is better insulated because it's got crud in the way, or an air pocket. So this is a failure. And this is a bleach tower, it has chlorine dioxide in it. And if you're familiar with chlorine and how nasty it is, chlorine dioxide puts it to shame. So you don't want to have a leak or a failure. And this is done, you know, totally without interrupting the process. So there are a lot of process and industrial applications for this, which don't fall under the building application, which is what we're doing here. All right. What building applications rely on naturally occurring surface temperatures? I'll let you volunteer this time. I'll make you volunteer this time. Okay. Any others? Not really. Delamination, you generally need to apply a transient. Air leaks, yes. Water if it's not trapped. What building applications require a thermal transient to be present or applied? We've sort of talked about some of them in not answering the first one. Trapped water, what else? Sorry? CMU, absolutely. Okay. So insulation gap detection, air leakage, some water detection if it's where the water can evaporate for the naturally occurring. The ones that require the transient either be present or applied would be some moisture, delamination, and spalling. A very brief punch list of other things to think about for infrared: product and process analysis, improvement and troubleshooting, product and process development, validation of modeling efforts. If you're doing modeling, you can use infrared to confirm and validate your models if you got a thermal component in your modeling. Non-destructive testing of parts. Yes?
To any extent, can you see reinforcement?
If they're large and shallow. If they're deep, kind of not. Because the concrete is actually fairly diffusive thermally, fairly conductive, so that the signature spreads out fairly rapidly. If you didn't want them near the surface, correct. All right, so non-destructive testing of parts, components, equipment, and there are medical and veterinary applications as well. Questions from you? Yes? Yes? There's some overlap in the applications. It's different technology. You're only looking at a surface with this, the temperature of the surface, with few exceptions, and exceptions that not really of interest to this group, I think. GPR is looking through. It's much more like X-ray. People call this X-ray, and it's wrong. It is not X-ray. It is looking at the surface temperature and or the surface radiation, but interpreting its temperature, looking at the surface condition and interpreting what it's telling you about what's going on behind it. Okay? Anybody else? Yes? Legally, none. ASNT, the American Society of Non-Destructive Testing, does have level 1, 2, and 3 grades for infrared thermography. The ASNT system I have some arguments with, because essentially at levels 1 and 2 your certification is by your employer to your employer standards as per ASNT 1- whatever. Level 3 is the only one that ASNT itself actually gets involved in the validation of. I'm self-employed, so I could, declare myself a level 2 by saying, here's my written procedure. My written procedure is that I should be able to tie my shoes in the morning, take them off at night, and own a camera. And that would allow me to declare myself certified as a level 2. Not standing here. Yes? I'm sorry? I don't believe this has any overlap with special inspections. So I think that's a no. No, I mean where this would overlap a little bit with code type work would be New York City Local Law 11, where you look where they require, I think it's a 5-year cycle, and you're going to have to correct me because, as I tell people, I don't know whether the Department of Buildings is. I don't practice in front of them, but I'm sorry. I'm trying to keep it that way, but
I do practice in front of them, and I don't know where they are.
okay, but Local Law 11 in New York City requires, I think, a 5-year cycle of inspection on walls of a given height to prevent issues like bricks falling out of the walls and hitting people. You could, as I showed you, define some of these without erecting scaffolding, but I don't think it would replace the local law 11 inspection as dictated by local law 11. It would, however, be something that would not be a bad thing to do first.
It would be a supplement, as I recall it, you used to do, and you may still be able to do visual inspections at a very cursory level. Every now and then, that may be a 5-year thing, you gotta drop the scaffolding. They won't, in the beginning, they said you used to be able to sit across the street and look with a pair of binoculars and say, yeah, that's good, that's not good, that's good. And this would supplement that and would do better with a pair of binoculars.
And it would help you say, you know, that area looks more questionable, that's one place we want to do the drop. So it would be economic for the company doing a local law 11 to have this done in front of it. You have a question? Underground tanks. The short answer is no. The longer answer is, depending on how deep the tank is, what's in the tank, whether the tank itself, if there is something in the tank, it is certainly a possibility. Papers have been published where you can find what they call disturbed earth. So for example, under the right conditions, you can fly over the prairie and see where the wagon train went 100 years before, because the earth is still more compacted where the wagon train was than 100 yards north. Papers have been published that say you can find graves. I actually tried that in Rockland County. I failed miserably. The person who's published a lot of this holds it very close to the vest. Some people say he's in fact not doing what he says he's doing. I don't know. But recognize, you know, if the tank is part of a process, so it has a different temperature because it's got hot stuff in it or cold stuff in it, then just like I showed you the underground pipes, I can show you an underground tank. If you're looking for abandoned tanks that are empty and they're doing whatever the ground is doing, you still have a possibility, depending on how deep they are, what they're filled with, if they're filled at all, and is it thermally different than the surroundings. You know, if they're filled with dirt, you got slim chance. If they're filled with water, or if they're empty, then through a transient over, you know, a 24-hour cycle, you got a good shot at it. One of the things that they do on above ground tanks is you can look at the tank again under the impact of the sun and cooling, and you can see where the liquid levels are. You can differentiate between the foam on top of the liquid itself, and the sludge under the liquid. And they use that, for example, to say, we need to shut the process down now because we got more than 20% height of sludge. And we're going to need 12 containers to take the sludge away versus the 2 containers we thought we would need. So they're ready for the shutdown in terms of having logistics arranged. So yeah, under some circumstances, yes. Any other questions? All right, in the case that you think, hey, that sounded neat and I could use it, our commercial department suggests this source. I have some brochures on the front table that are specific to real estate type stuff, buildings and business cards. I'd appreciate it if you take those. I will probably be sending you an email with a link to a survey of how I could do this better, different, or worse. Service mark, as opposed to trademark.
And what is that?
It's like a trademark, but it's a service rather than a thing.
And it's something that existed forever?
Well, I don't know about forever, but it's been around. And as part of the survey, I will also ask you to tell me, hey, please contact me, and I'd be glad to. So, thank you for your attention.